Hello again, secondary educators. Now that we have built the whole numbers and we used those to build the integers, it is time for us to take the next natural step and build the rational numbers. And we're going to do it in a very similar way to how we built the integers in the first place. We are going to put the set F for fractions, and it's going to be the set of ordered pairs A, B in Z cross Z, where B is not 0, and it will be obvious soon why B cannot be 0. And we are going to say that the ordered pair AB is related to the ordered pair CD if A times D equals B times C. And it should be obvious. We say that A over B is equal to C over D if AD equals BC. And we know that the second coordinate in the ordered pair cannot be 0 because, right? So we're going to represent the fraction A over B with the ordered pair AB. Why? Because we already have ways to deal with the integers. So we're going to build off of what we already have with the integers. We are going to say that the set Q of rational numbers is the set of equivalence classes of F under that relation. So this is fairly straightforward because when we talk about this fraction, we want to make sure that this is the same fraction, and this is the same fraction, and this is the same fraction, and so on. But they are. They're all part of the same equivalence class, because if you take any two of them, they satisfy this relationship, and so they are related. So all of the ordered pairs representing all of those fractions belong to the same equivalence class. They represent the same number. So we have a construct by which we can talk about fractions being equivalent. I'm going to throw this side note out there. This is our first side note of the semester. La! So here's our first side note of the semester. The ordered pair AB is in the set F. The ordered pair AB is not a rational number. The equivalence class of that ordered pair, that's a rational number. The ordered pairs themselves are fractions. They are not the rational numbers we're talking about. The rational numbers we're talking about are equivalence classes of those ordered pairs. And we better ask the question, when is one rational number less than another rational number? Well, we say that the equivalence class of AB is less than the equivalence class of CD if BD times BC minus AD is positive. That's what we say. And so I would encourage you to pick two rational numbers, one that you know is less than another. Try the definition. Make sure you get a feel for it. Why don't we just say, well, if this is positive, like why do we need these to be in the mix? What could go slightly awry that would make us want to consider that? So pick some pairs of rational numbers where you know that one is greater than the other. Play with the definition. Make sure that you can be confident that this condition does what we say that it does. In this way, we generate all of the rational numbers you could possibly want to generate. We just treat them not as one integer divided by another, we treat them as ordered pairs, and we use multiplication to help sort out who's equivalent to whom. Hopefully this is helpful. Hopefully you can see that rational numbers are really a thing and there's a way to deal with them in a rigorous way. And that helps you know that all the arithmetic we're about to do is on a solid footing. Thanks for sticking with me. We'll see you soon.